Okay. Afternoon, everybody. This is, I've lost count, maybe our third Spatial Stats seminar of the year, maybe the second, I can't remember. Anyway, no, it's definitely our third.
It's the third.
Thanks, René. And today we have the honor of René Stander. She is in limbo. So she's got her letter for graduation, but she hasn't graduated. So she hasn't walked across stage. So you can't call her doctor, but she's doctor. Okay. So you can pretend to call her doctor, but not in any legal manner at this stage. So René was supervised under myself and Professor Din Chen at the University of Pretoria. And she has made herself an expert in spatial stats. So we thought it good that she could come and present to the community on her spatial stats experience and the work she's contributed. So I'll hand over to René. And then if you have any questions as you go, you can put them in the chat. And at the end, welcome to ask your questions out loud as well. Thank you, René.
Thank you so much. So good afternoon, everyone. So today I'm going to talk a little bit about what I did in my PhD. So it is quite a mouthful, but I'll try my best to make it as digestible as possible. So my topic was multiscale decomposition of spatial lattice data, specifically for hotspots predictions. So just first of all, a spatial hotspot, that is an area in the domain where the occurrence of a certain event is higher than surrounding areas in the domain. And why do we want to predict hotspots? So by being able to identify areas that's at risk in the domain, it can help local authorities to implement and prioritize interventions and preventative measures. So being able to detect such problem areas early will have impacts in the fields of criminology and epidemiology. So in criminology, there's quite a lot of predictive policing literature, and they all refer to like the early detection can help police authorities to prioritize resources, especially like in South Africa where there's not always enough resources. And in epidemiology, if you think about the recent COVID pandemic, being able to identify these areas can help with hospital preparedness and also mobility restrictions as we had with the lockdowns. So just the structure of the thesis. So on this side is more, so these are the hotspot detection methodology. And then on the other side, we have geostatistical methodologies. I'll get into more detail on how it fits into each other as we go along, but on the one side with the hotspot detection and on the other side with the geostatistical, it at the end flows into each other for a hotspot prediction. So each of these blocks formed a chapter in my PhD. It was also presented as a paper. So I will go through them. First, go through the discrete pulse transform on the lattice data, then hotspot detection, and then I'll jump over to the geostatistical measures, and then at the end, how it all ties together. Okay. So before we get into the details, just reminding ourselves what is spatial lattice data. So that is when the domain is divided into predefined regions. And then the data is aggregated to these subregions. So you have an observed value for each subregion instead of individual points. This type of data is quite popular in the criminology and epidemiology literature, as it's for protection of information as well. So there's no sensitive information aggregating the data up. So these subregions can either be regularly or irregularly shaped. So on this left-hand side, that's regular regions, and so it's perfect blocks. And on the other side, you have irregular lattice data. That is administrative boundaries, districts, municipalities, provinces, you name it. We all know it. Okay. And then regular lattice data is especially images. Okay. It's just it's an image. So when working with lattice data, the first thing to define is a neighborhood. So that is basically how these regions fit into each other. The most popular one is contiguity neighbors. So basically just saying if the regions share a boundary, they are a neighbor. And these are usually denoted with a spatial weights matrix, where n is the number of regions, so it's just n by n. And in entry ij, it will be non-zero if region j and region I is a neighbor. Okay, that's the gist of what's happening here. And just an example, so if we look at the regular lattice, region 1 and region 2 is neighbors because they share a boundary. So in the contiguity matrix, in row 1, column 2, so in entry 1, 2, there will be a non-zero value saying they are neighbors. Okay. And with the irregular lattice, it's the same. Just the structure of the neighborhood is just a little bit different. Yeah. So now we've got that out of the way. If we move on to how the DPT can be applied on lattice data. So the DPT stands for discrete pulse transform. Okay. So the DPT has been used on images before to extract salient features. So what is a salient feature? That is an important part of the data. So in an image, let's say it's an image of a cat, the salient feature might be the cat, and the rest is just background. Now in spatial lattice data, a hotspot can be the salient feature. And as the discrete pulse transform has been applied on images, and images is a special case of lattice data, the extension for the DPT to the lattice data with irregular regions, it flows quite intuitively. So in the first part of my PhD, that was what we worked on. And this was also published as a proceedings paper in 2021. So the DPT, okay, I'm going to just quickly say here, I'll rather focus on pictures and examples. So it works on Lulu operators, LN and UN operators. So the LN operator, it's minimums of maximums, and it smooths local maximums in the domain. The UN operator smooths local minimums in the domain. And then the DPT is the recursive application of these operators. So you first apply L1, U1, and then on the smoothed data, L2, U2. And it goes on up to the end. Okay. But let me make it clearer with an example. So let's say we have this regular lattice, so image for now. And if you represent it with the 3D histogram, it will look something like this. So on the upper left-hand corner, there's a 5, which clearly from the histogram, you can see that it is a local maximum. Yeah. And it's a local maximum size 1 because there's only 1 pixel there. Then if we apply the L1 operator, this local maximum of size 1 will be smooth. to the closest value. So in this case, the closest neighboring value is 4. So it will be smoothed to 4, and it will look like this. Okay. This part that we cut off, so that little pixel, it's saved on the side as a pulse. Okay. And then if we take this smoothed image and we apply the U1 operator, so that is smoothing a local minimum of size 1, which is this block over here, we smooth it to the closest value. So we're bringing it up to 2. And then now it looks something like this. And this part that we filled up now, we also save that as a pulse on the side. So everything that we do, we smooth, we save on the side. And that is where our information is going to be. Okay. So if we continue with this, if we smooth a local maximum of size 2, which is these blocks over here, and then the local minimum of size 2, and then at the end we get a completely smoothed image. Okay. Now remember, every time that we applied one of these operators, we saved that part as a pulse that we cut off or filled up. So those pulses, if we sum them all together, so we reconstruct all of them together, we get this image. Okay, so that is decomposing the data fully. Okay. Now applying the DPT from first principles. So that is with these two equations. Is very complex. It has a complexity of order n to the power 3. Work has been done to ease this complexity with the Roadmaker's algorithm and later on the Roadmaker's Pavage algorithm. So these are graph-based methods to ease the computation of the DPT. And so that you don't have to implement it from first principles. So it does help with the implementation. And in our work, we implemented the Roadmaker's Pavage algorithm. But because most of the spatial packages and work is in R, we did it in R instead of in Python, where all the previous implementations were. So in that proceedings paper of mine, there's nice steps and pictures on the exact implementation, which I don't have time to repeat in this seminar. So now that we have all of these pulses and parts of the data, we need to get it in some sort of way that we can work with it and see actually where is the information, where can we maybe detect the hotspots. Okay, so for this we use the HT index. So the HT index stands for head tail breaks, and this basically creates intervals that's more sensible intervals on data, especially very skewed data. Okay, so I'm not going to go through these. I'm going to skip to the example. Okay, so let's say we have pulses of the following scales. So scales is just another word for sizes. So we have the following sizes of the pulses after the decomposition. So how it works is then you take the mean of this, which is 2.5, it's somewhere over there, and then you see more than 50% of the number of pulses is less, or the number of scales is less than the mean. So we cut off the lower parts and we only continue with the pulses greater than the mean. Okay. And then so we only continue with 5 and 7, then the mean is 6. Okay, so 50% is then less than the mean, and then we can stop. So the moment we have more greater than the mean than less than the mean, or the same number, we stop with the implementation. Okay. So then we can use this as intervals. So in this case, our intervals is 1 up to the first mean, and then the lower value again up to the next mean, and then whatever was left at the top, which is 7. Okay. So we have 3 intervals in this case. Then later on, the multiscale HD index was developed. So it's a recursive application of the HD index. So the HD index is applied once, and then with the multiscale HD index, you'll apply the same procedure again on these intervals until there's all of them, there's like 1 value left. Then you stop. And then this actually ends up in a visualization like this. So it's a tree structure. Okay. And then that's the visualization of the HD index, which you can, so it's intervals now of the decomposed data. Okay. So we decompose the data. Then, if we want to do hotspot detection, we have to quantify this saliency in the data. So we need to know in which of these intervals, where's the information, where's the hotspot, okay? And that is what we did in this paper. So this paper is recently published in the South African Statistical Journal. So if there's anything you wonder about while I'm speaking, you're more than welcome. There's more details in the paper than what I'm going to say now. Okay. So with the hotspot detection method, we did the decomposition as I just explained. Then after the decomposition, we quantified the saliency, and we used the spatial scan statistics for this. So this is a likelihood ratio test, and we did that for all the pulses in each node in the HD index graph. So those intervals in the HD index that we created, each of them we partially reconstructed. So if it's the interval 1 to 4, we would reconstruct all the pulses of size 1 to 4, just those, not the entire image. And then we would apply this likelihood ratio on those pulses, on that partially reconstructed values, and get a test statistic, which is just the maximum of the likelihood ratio. And we would do that for each one of the nodes. And then at the end, we take the one with the maximum value, with the maximum likelihood, and partially reconstruct that. And then, so that is then where our information is. And then we standardize those values, and all of the regions with a value of more than 1.96, that's our hotspot areas. Okay. Then just another important thing here is we only use the positive pulses, so only the local maximums that we smoothed, as that's where we expect our hotspots will be. Okay. One thing I just quickly want to mention, I didn't add a slide on that here. We did a quite extensive simulation study with the details is in the paper, where we compared this hotspot detection method with Geeta's ORD, which is a very popular method in spatial statistics. And this method outperformed it every time. And with further investigation on why it's actually that is Gieter's odd is not good when you have a small number of regions because it works with the normal approximation. So when it doesn't have enough regions, it freaks out. So yeah, so this is where our method actually performs much better than Gieter's odd. Yeah. Then just an example of an application. So these are all COVID cases in South Africa at a municipal level. Okay. So as you can see, there's quite high values here in the Gauteng region, and then here in the Cape Town region, as well as Durban over there. So then we applied Gieter's odd and our method on this data for comparison. Okay, so on the left-hand side is the hotspots that this method detected, and on the right-hand side is where Gieter's odd detected hotspots. Okay, so you can see that it does detect larger regions than our method, but you can see that it did miss, for instance, this Cape Town municipality in Gieter's odd. And then just another validation. These plots are just the index of the spatial region. So there's no spatial information here. And the value of the spatial region on the y-axis. Okay, and you can actually see that Gieter's odd missed some of the spikes, and it also did many false positives. Okay, which is something that we try to avoid in our method, especially in the case of COVID. Like you don't want to detect a region as a hotspot, and then it's actually not, because you don't want people to panic unnecessarily or restrict mobility unnecessary because of the economic implications. Okay, so that is it for the hotspot detection part. So just keep that in the back of your mind, because now I'm going over to the geostatistical methodology in this whole work. Okay, so kriging is an interpolation method that's used in geostatistical data, and it can predict measurements at unobserved locations. So geostatistical data is point data where you take a measurement at a specific point and at sample points throughout the domain, and then you try to predict the values at unobserved locations. If you think about the weather, you have weather stations where you take measurements and you try to predict it at locations where there's not weather stations. Okay. So the main difference between geostatistical data and spatial lattice data is the observational type. So as I mentioned, geostatistical data is points, and lattice data is discrete regions. Okay. Geostatistical data can happen continuously throughout the domain. So with lattice data, the events still occurred continuously throughout the domain, but it was aggregated up to an areal level. So there has been some work done with the application of geostatistical techniques on spatial lattice data. And in these instances, they have used the centroid of the areal unit as a representative point. But by taking an areal unit and represent it with a single point, fails to take the size and the shape of the areal unit into account. And then this paper that I referenced here, they have actually started investigating the use of multiple points of representing the lattice data for variogram estimation. Okay, so we continued on that. Okay. So then a variogram quantifies the spatial variability, and this is used in a model such as kriging for the interpolation. Okay. The paper on this work is currently under review, so we are still waiting feedback on this. Yeah, so let me continue then. Yeah. So just an example of what variogram estimation does. So on the left-hand side here, this is geostatistical data, built-in data in R, of metal measurements in topsoil from the Meuse River in Europe. Okay, so if you fit a variogram on this, these black dots, that's your empirical variogram that you calculate, and then variogram models are then fitted to the empirical variogram, and then the variogram model is used in something like kriging. So there's 3 different variogram models, the exponential, Gaussian, and spherical that we've used here. There are others. So there's 3 parameters that we consider. So it's the nugget. So that is when your y-intercept is not 0. And then the next one is your range. So that is where the distance at which this model converges. And then the sill is the value where it converges. And you can see there's different nuggets and sill values for each one of the models. Okay. And then theoretically, the sill value should convert, the value of the sill should converge to the variance of the data. Okay, so the variance of these points. Okay. So what we did for the variogram on lattice data is, because we want to quantify the spatial, we want to quantify the spatial variability. Okay. So if we have lattice data, the little toy example here on the left-hand side, and we use the centroids as the representative points, this is the variogram that results. Okay, so the points are my empirical variogram again, and the lines are the model. Okay. I haven't included the performance measures here, but it is in the paper. But you can visually see that it's not fitting well. Okay, and especially one thing with the variogram is in the lower distances, you want points, because the way the variogram fits with the smaller distances are more important than with the larger distances. Okay. And there's no points small distances apart, but because you have this buffer around all the points because of the aerial data. Okay. So this is one big problem with using only the centroids. So what we explored is simulating additional points. So you simulate more points than just the centroids. So I used 2 sampling methods. So the first is non-aligned, and the second is random sampling. So non-aligned is basically like regular, but it's just not in perfect lines. Okay, this is so that we can cover the entire region, and so that larger regions have more points than smaller regions. And then with random sampling, we are adding variability in the distance measures, or distances between the points. Okay, now we have points, but now each of them needs a value. Okay, so a lot of thought went into this, and we tried a lot of lot of ways, but it actually boils down to the method that captured the variability the best was to just give the point the value of the region it falls into. Okay. There's literature on changes of support, so especially of lattice data. There's a method called area to point kriging, which takes aerial data and estimates values from it. The reason we haven't used that is because the main goal of this variogram estimation was just to capture the variability in the lattice data to be used in a kriging model. Okay, so we didn't want to add unnecessary complications, and we just wanted a simple, fast method that will capture the variation. We have tried a kernel estimation to get more variability in the points, but I've included it in the paper. I haven't included it here. It didn't work. So this ended up being the better way. Okay. And then we estimate a variogram on these points. Okay. And it actually does present us with a better variogram. And all of these variogram models actually in the lower distances fit quite well. Okay. These are not RMSE values. I forgot to update that, sorry. These are weighted mean squared error values. So it gives, the weight is then the inverse distance. So it gives a larger importance weight to these points in lower distances than those further distances, because it's more important that it fits well with the points close to each other. Okay. So when we use just the centroids, you can see the values are quite high. But when we use this method, it did bring down the weighted mean squared error quite substantially. Okay. Then, just to add a little bit more robustness, we used a resampling approach. So we didn't stop here with the estimation of the variogram. We actually did a resampling approach to get a final variogram, because you don't know if your sample points were actually at the correct locations, and just to add a little bit more certainty in this. So we sampled 85% of the sampled points at each iteration. We have repeated this most is 1,000 times. And then we fit a variogram in each iteration. And at the end, we take the average of the parameter values for our final fitted variogram. So this red line is then, that is the variance of our aerial data. So we can see that it still does get to the aerial, the variance there. Okay. So how does this all then fit into the hotspot prediction? So with the hotspot prediction, we are considering spatial data over time. Okay, so we have spatial temporal data. This type of data is good for the analysis of, the analysis of such data is crucial in identifying the trends and the patterns, okay, of crime and diseases. And considering the observations over time, a spatial temporal kriging is a good interpolation method for these, as it can predict measurements in unobserved locations in time and space. So with normal kriging, we had we could predict at unobserved locations, but now with spatial temporal kriging, we can also predict at unobserved locations in time. So we can forecast. And it's a flexible and effective method for predicting space-time patterns. So this is what spatial temporal data, what it looks like. So if we just consider this small data set with 6 time steps, okay, so we have observed data at each time step. Okay. We can represent this as a time plot for each region. Okay, so you can see this. Okay, it's difficult to see, but there are some of them with upward trends, some with downward trends, some with almost no trends. Okay. So in this hotspot prediction, we propose the use of a geostatistical technique. Okay, so this is called the geographically and temporally weighted regression spatial temporal kriging. That's quite a mouthful, but we want to predict the observations at the next time step. So we use this model to fit from time step 1 up to time step 5, and then forecast to time step 6. Okay. So how this model works is with the spatial data, it's usually, especially with the kriging, it's usually done as a 2-step process. So we have a drift component, which is modeled with the geographically and temporally weighted regression. And then the residuals of that is modeled with the spatial temporal kriging. Okay. And that is where our variogram estimation is going to come in handy. So the geographically and temporally weighted regression works as follows. So we have an intercept. In our case, we didn't consider any covariates, okay? And we have our residuals, okay? So then our intercept parameter is estimated with this equation, okay? So it looks a lot like normal regression, linear regression, but we do have the weight added. And this weight is where our spatial information comes in. Ooh. So we estimate this for each space-time observation. So each observation in space and in time. Okay. So when I say that, you should just think computation. So everything is computational with the spatial temporal methods. Okay. So this weight is actually calculated as, so it's a distance in space and a distance in time. Okay. That's considered. So then if we fit this model, it gives estimated values somewhat like this. Okay. And you can see that now that the time plot, sorry, that should be time, is now smoothed. You can see the upward trends, you can see the downward trends in the data. Okay. So with this now, the residuals are then modeled. So these are now the residuals of that geographically and temporally weighted regression. And those residuals are then modeled with a spatiotemporal kriging. So we use the variogram that we just did. We are going to extend it to spatiotemporal, so not only have space, so in one dimension, we actually have space and time. Okay. And yeah, so we, instead of having a 2D graph, we're going to have a 3D graph. Okay, so we still simulate additional points and assign it the value the region it falls into. And then we estimate the variogram, and it looks like this. Okay, so it's actually a 3D representation. For the variogram as it is now, for the spatial temporal one, we didn't do the resampling. We just did the estimating of the variogram ones. Because of the computation, you can imagine it's very computational because it considers distance in every combination in space and time. It's very computational. So then for the prediction, so now we modeled the drift component, we modeled the residual component. Okay. So the drift component is then forecasted using this Holt-Winters exponential smoothing. And for the residual component, we use spatial temporal kriging. And then it's actually just added together. Okay. So for this small data set, then the observed at time step 6 was something like this, and the predicted, this is the predicted one. Okay. So I didn't include the differences here now. I'll show you when I do an example. Okay. So these are it's just a plot, no spatial information here. So it's just the index on the x-axis and the value on the y-axis, and just original versus prediction. Okay, I added the line, you can just see better which one is lower, which one is higher. So the prediction does follow the original representation well, but there are some of them that's lower, under-predicted, over-predicted, but that's a statistical model won't ever be 100% perfect. Okay. Now the hotspot detection comes in on this predicted values. So we are going to use the hotspot detection method on this predicted values, what we predicted. Okay. So just for a comparison and evaluation of the method, we do it on the observed values as well, because that is what we have. Okay, so this method is then applied to what we knew was the true and what we predicted, okay, at time step 6. And you can see that it did predict the same hotspots. Okay, and it's also seen in this plot, the identified hotspots. And so at this stage, we weren't so concerned in how the model forecasted, because we were more concerned in detecting the hotspots. Did it detect the correct hotspots? Because we wanted to predict that. Okay. Then just to show you that it works on other data as well. So these are COVID cases at district level in South Africa. So I didn't use the municipal level as I did before because of the computation. So we used week 24 to 28 to fit the model to try and predict the hotspots in week 29. So these are the forecasted values. Here, forecasted values. Again, with the same line plot to show that it does follow the same trend, just somewhere it's less than the actual value and vice versa. And then this plot is actually the difference between the observed and what was predicted. Okay, so it's overall the values are low. It's just here in the upper right Limpopo region here. But in future work, we'll still look at what happens exactly there. And then if we detect the hotspots on the observed data, what we had, what we knew, and on our forecasted data, it did predict the same hotspots. Okay, so the prediction does work in this instance. Okay. Then just what's next? So there's still always some work that we can improve on for the hotspot detection, to extend these to warm spots and cold spots as well. So warm spots is the region is not so the events are not so high that it can be classified as a hotspot, but it is higher than the other regions. So being able to identify that can assist in the hotspot prediction. And then variogram estimation. So when we simulate those points, we can use covariates. So for instance, population. So where there's a denser population, more points can be simulated, etc. And then the hotspot prediction is, so there's something called emerging hotspots analysis. So we can actually go into more detail into the trends and also use that as a risk, as a early warning for hotspots. And then also the prediction of more than one time step ahead, and then the calibration as new data arises. And then the fast implementation of a spatial temporal variogram that needs quite some work still. And then also the inclusion of covariates into the modeling of the drift component. So not only using the intercept, but actually considering other covariates. Okay, and that is it from my side. Are there any questions?
Thank you, René. Your lecturing skills are top-notch. It was very nice and clear.
Thank you.
Any questions? Yeah. Any questions? Comments for René? Nancy?
Hi, René. Thanks.
Hello.
Can you hear me? Okay, yeah.
Yes,
So
I can hear you.
Perfect. Thank you for that. It was really interesting. I was just wondering more on the sort of data checking side of things, how you address that issue on stationarity. If you looked at the anisotropic behavior, was that included in your modeling process at all, or was it sort of this the first step and the next steps will also include that?
So we didn't look at anisotropy. I haven't really seen that in lattice data, but that is actually quite an interesting. I haven't considered the anisotropy, but that can be, I really think, can be a nice addition sometime. Then the stationarity. So the reason, let me just see where I can get a slide. Okay, yes, yeah. The reason why with the spatial model, this model splits it into two parts is for stationarity. So you first model this deterministic drift, which is actually then your that is where more of your spatial information is. And then with the residuals, your residuals is then stationary. So you can use something like reading on that. I hope that makes sense.
Yeah, perfect sense. Thank you.
So very interesting question, Nancy. Well, I also haven't thought about anisotropy with lattice data, but it's very valid.
Yeah, I haven't seen any
Don't think-
literature on that. If I think about it,
Hmm.
I'll write it down.
I've written it down as well.
Ah, you can add me you can put me in the acknowledgement.
No, Auntie, we'll just bring you in. You can do it with us.
Yes.
Let's see. Sorry for the banging. There's some building going on behind my wall here. Let's see. Safaris says, might need to contact René. I had same issue and mostly binary outcome and small area. Yeah, absolutely. Give us a shout if you want your email address. We can have a chat. Herbert says, thanks, René. On the resampling approach slide, the second box plot with outliers, do they have any implication or do they serve as a signal?
That's an interesting question. Sorry, can you maybe just repeat the question again?
So on the resampling approach slide, the second box plus for the outliers, I think that one, you see the one that's got the most outliers there. Do they have
Yes.
any implication or do they serve as signal? So maybe there's something happening there.
Yeah, I think it's an interesting observation, and I haven't thought about that specifically. I do think those might have an influence, and I think it's maybe those points that were sampled. But I do think like a deeper investigation on exactly what happens, like why are the outliers there, might be good. I think because we take the mean of the parameter values, I think it is scaled or taken into account a little bit. I don't know if that answers the question.
Yeah. No, I think you're right. But I think it is interesting to see why that one happens to be more
Yes.
than the others.
Yeah.
The nice
Maybe also in what instance does it happen?
Yeah.
Is there data, something in data that makes it happen?
Yeah. Tefera asks if we can have the slide. I'll answer for you, René. So the first two bits that she's published, obviously you're welcome to go look at the papers. They've got all the details, but the second stuff she's still publishing. So not much we can share with you. When she's published it, then we can share the whole paper with you.
Yes, yes. So maybe I'll just, those slides where I added this references on my papers.
Yeah, maybe you can leave it up. They can take a screenshot.
So this is the proceedings paper, and then the hotspot detection paper.
Sibu, you've got your hand up?
Yeah, I do. Thanks, René. It's a very interesting talk. The one question that I do have was just on your resampling approach. I was wondering more about that, specifically since you do have spatial data. Did you take into account spatial dependence, or for now you just assumed kind of like independence in your resampling?
So with the resampling, let me just go to that slide. It's better if I see it than I talk in the air. So if I understand your question correctly, that is the reason for the 85%. So there was a paper some time ago, it wasn't too long ago, that actually said they actually determined how many points should you sample to what's the word now, to keep the spatial structure in your data. And they actually came up with 85%. That's the minimum number that you should sample from your point data so that you keep the same structure, so that the spatial dependency is preserved.
Okay. And just on the more practical side, you did comment that the approach is a bit computationally, let's say, expensive. And I was wondering how would one scale this approach? For example, if you're looking at satellite images, so you're obviously dealing with very large data sets. What are your thoughts on being able to leverage your methodology for those data? Is it just a matter of, improved computational infrastructure, or could more be done from a methodology perspective?
So are you specifically, to which part are you referring to? Are you referring to this model?
Yeah, your combined, your geographically weighted kriging approach.
Yes. Okay. So the big computation here is with the kriging parts, with the variogram estimation. So I think if one can, that for spatial temporal variogram, I think if one can have a way of coding that better. I've used the built-in function in R, and even in the documentation they said it's not coded very nicely. So I think a parallel processing might help there. The geographically and temporally weighted regression, that's computational, but not bad. And because you calculated for each combination, to code it in a more efficient way, like the first thing I can think of now is a parallel processing. It can be done because it's not something that's iterative. For instance, the DPT can't be parallelized easily because it's an iterative process where this is not iterative. So there will be some way that you can make it faster. But I haven't like done it yet, or give it a lot of thought at this moment.
Cool, thank you.
There was a question here in the chat from Herbert. I'm not sure, maybe you'll understand it, René. Just wondering if these approaches would work with repeated cross-sectional data like DHS. And then, I'm not sure what DHS is, in trying to assess temporal trends given limited longitudinal data. So, maybe understand better.
There's some words that I'm also not 100% sure.
Demographic health survey. Okay. So it's longitudinal health data. So
yes.
Temporal trends, and obviously you'll have a spatial effect there.
Yes. No, I'm sure it will in some way work. If you have a trend, because that's exactly what we are trying to do. So we are trying to model and forecast the trend. And that's also where the so it will, if you just don't want to do the hotspots, then you just stop before the hotspot detection. So you can still model and with and forecast with this.
Yeah.
We were more interested in will it be able to detect the hotspots on the predicted values correctly? So there's still some work that we can do on the forecasting and the model to make that better.
Yeah, absolutely.
But I'm sure it will fit.
I also think so. So Herbert, we can do that. Give us a shout. You can join us with that. We can do that as well.
Yeah.
Okay. Any other questions from anybody? All right. So watch out. So René's 2 papers are published. The last paper on the variogram is still is under review, and the spatial temporal stuff we're still perfecting because of the computational aspects. But René's here, I'm here, we're not going anywhere. So if anyone ever wants to, has a thought or a suggestion or wants to work on something, very, very well, happy to do that. Oh, okay, so this was our third Spatial Stats seminar. We will have at least another 3 planned. Renata, is Renata still here, if I'm correct? And
yes, definitely.
And then I'm going to just announce it. I think we hinted at it at one of the last seminars, but we have got the SF Network's Lucas van der Meer. We have convinced him that he should come to South Africa in November to the SASA conference. So he's going to be a speaker there and he will do a workshop. So if you saw his Spatial Stats seminar earlier in the year, you get to see him in person later in the year. So please don't miss out on the SASA conference at the end of the year. It will be officially announced with the website and everything later in June, early July. But it obviously, our SASA conference always happens, and it will be the week of 18 November this year. So in Stellenbosch, hosted by the University of the Western Cape. So don't miss out on that. And keep your eye open for our next seminars that are announced. Okay. Thank you, René. We really appreciate your time and your effort to put your slides together, and of course, all your work that you did in your PhD. When you see her at SASA, you can call her doctor. Until then, she's just René. Proud of her.
Thank you so much for inviting me.
Oh, it's a pleasure, René. Have a lovely day, everybody. Bye.